Welcome to the workshop. Today, we're cracking open Algebra's toolkit. We're going to see how, with just a few core tools, we can build some incredibly complex mathematical structures, and then, just as easily, break them right back down into their simplest parts.
You ever look at something like this on a page, and your brain just kind of shuts down? It looks like a total jumble of letters and numbers and powers. But what if I told you there's a simple, really elegant structure hidden inside all that this wasn't random at all, but was built piece by piece from something much, much simpler?
And that's exactly what we're going to do. We're going to assemble the toolkit you need to not only understand that expression, but to build and take it apart yourself. And the best part? It all starts with just a few basic rules. Okay, first things first. We have to learn the language. And in algebra, that language is all built on powers. Think of them as the fundamental grammar. Once you get how they work, the rest of the conversation starts to make a whole lot more sense.
So let's start with the most basic tool in the box. When you see a term like a to the power of n, we're just giving names to the parts. A is the base, that's the thing we're multiplying, and n is the power, sometimes called the index. It just tells us how many times to multiply that base by itself. That's it. That's the core idea. Simple, right?
Now, these three laws, they are the bedrock of everything we're about to do, and they're super logical. If you multiply two terms with the same base, you're just adding to the total number of multiplications, so you add the powers. If you divide, you're kind of canceling some out, so you subtract the powers. And if you raise a power to another power, it's like a repeated addition, which, is just multiplication. These are the non-negotiables of our toolkit.
All right, we've got the grammar down. Now let's start building. This is the construction phase, where we take simple building blocks, like expressions and brackets, and assemble them into something way bigger and more complex. And there's a name for this process. It's called expanding. When we take those neat little bracketed expressions and multiply them out to get one long expression, we're expanding them. We're basically laying all the individual pieces out on the table.
And here's the systematic way we do it. To expand these two brackets, every single term in the first bracket has to multiply every single term in the second one. As you see here, we multiply the f terms, then the outer terms, the inner terms, and finally the last terms. Once all the parts are multiplied out, we just do a little cleanup by collecting any like terms together.
And this process totally scales up. If you expand three brackets together, you get what's called a cubic expression. Hey, remember that big, scary expression from the very beginning? That was just the result of expanding 2x minus 3y 3 times. See? It's all just construction.
So we've mastered building things up. But, any good toolkit needs a demolition tool, right? What if we find a complex expression out in the wild? Can we actually work in reverse to see what simple parts it was made from?
This is basically the art of reverse engineering. Can we deconstruct the final product to find the original blueprint? Well, as it turns out, yes, we absolutely can.
And the tool for this deconstruction is called factorizing. It's the direct opposite of expanding. Instead of multiplying brackets out to get a long expression, we're taking that long expression and putting it back into its original brackets. We're finding those original building blocks.
This slide right here, this shows the whole relationship perfectly. It's the key idea. Expanding takes you one way, from the tidy brackets on the left to the long expression on the right, and factorizing, well, it takes you right back home. They are literally two sides of the exact same coin, just different directions of travel.
And here's where it gets really clever. When we're deconstructing or factorizing, we can start to look for common patterns. These are like shortcuts that let us see the original structure way more quickly. And one of the most elegant ones is this.
The difference of two squares, it's a classic. Anytime you see a squared term minus another squared term, you know instantly, without even thinking, that it factorizes into two brackets, one with a minus, one with a plus. So x squared minus 49, which is really just x squared minus 7 squared, cleanly becomes x minus 7, x plus 7. It's a beautiful time-saving pattern.
All right, we have the core toolkit for building and breaking. Time for the final upgrade. Let's add some advanced tools to our kit that let us handle powers that aren't just simple whole numbers.
It turns out, those same laws of indices we learned at the very beginning can be extended. They also work perfectly for negative numbers and for fractions. And this unlocks a whole new level of flexibility.
Let's just walk through this table. Look at that first row. A negative power doesn't mean a negative number. No way.
It's an instruction to flip the term, to take its reciprocal. So a to the power of minus n just becomes 1 over a to the power of n. Now for the fractions. The number on the bottom of the fraction, the m, tells you what root to take. So a power of 1 over 3 is a cube root. Simple. Finally, if you have a full fraction like n over m, it's a two-step dance. You handle the root first, that's the denominator, and then you apply the power, the numerator.
And here's a crucial detail, a little tripwire that catches a lot of people out. A power of 1/2 means the positive square root, not plus or minus, just the positive 1. So 9 to the power of 1/2 is 3, period.
So the key takeaway here is that these aren't really new rules at all. They're just logical extensions of the ones we already know. And they give our toolkit way more range and power for both building and breaking down expressions.
And that's really the whole journey, isn't it? We started with just 3 basic rules for powers, and from there, we learned how to construct these complex expressions, and then how to reverse the whole process to find the simple parts hidden deep inside.
So you see, algebra isn't really about memorizing a bunch of rules. It's about understanding a system. It's a language for describing patterns. We've uncovered a few cool ones today: expanding, factorizing, the difference of two squares. The real question is, with this toolkit now in your hands, what patterns will you go on to discover next?